I'm going to take a look at a handful of ways that Euler's formula can be used. So exponential functions. Clearly it's going to be useful with exponential functions. We said e to the iota theta, but of course we could add 2 pi k on and we'll be back at the same spot. So we could write it like that, but that would be the same as cos theta plus I sine theta, because every time you add 2 pi on, you're going to be back at the same spot and back at the same spot. So the power doesn't just have to be I theta to be cos theta plus I sine theta. It could be I theta plus any multiple of 2 pi I would also be that same complex number. So there's ei to the theta plus 2 pi k. We're saying that's equal to I theta. Basically what that's saying is it's a periodic function, just like a trig function. So every 2 pi, you're back at the same spot. So it's periodic. Trig functions. Again, there's that lovely link between Euler's with the trig and the exponential. So clearly it's going to be useful for trig functions. We know these identities. Remember those ones? We proved z to the n plus 1 on z to the n, 2 cos n theta, and then the similar one for sine. Let's rearrange those. 2 cos n theta, I could now write as e to the n theta I, because that would be z to the power of n, plus e to the minus n theta I. That would be z to the minus n. Divide by 2, we get an expression for cos n theta. And we could do a similar thing for sine, divide by 2i in this case, and we get a result for sine n theta. So now if we have to prove sine squared plus cos squared equals 1, there's the simplest trig identity that we have. So a way we could now prove that, I could substitute in, if we wanted to, sine and cos. So sine squared would become 1 on 2i squared, e to the iota theta minus e to the minus iota theta squared, plus cos squared, 1 on 2 squared, e to the iota theta plus e to the minus iota theta squared. Expand that out. We've got some terms there that cancel, and I end up with a quarter times 4, which is 1. So I prove sine squared plus cos squared is 1. I don't know that that's my preferred way of proving that result, but you could. Let's try a different one. Sine cubed theta is 3/4 sine theta minus 1/4 sine 3 theta. Okay, well sine cubed theta would be e to the iota theta minus e to the minus iota theta over 2i cubed. Expand that out. Okay, I'm looking at what I'm trying to prove, right? Let's group together the powers of 3i theta and the powers of I theta, or the negatives and the positives. Group them together. They're both over 2i. So what we've got there is 3/4 sine theta minus 1/4 sine 3 theta. Oh, maybe that's a quicker way of doing that one. How about this one? Our product to sums formula. So 2 sine alpha cos beta is sine alpha plus beta plus sine alpha minus beta. 2 sine alpha cos beta would be 2 times, substituting our result for sine, substitute our result in for cosine, expand that all out, and we can see in the powers we get a lot of alpha plus betas and alpha minus betas when we use our index laws, and they're all over 2i. Break it up into 2 fractions, and we've got it. There's sine alpha plus beta plus sine alpha minus beta. A little bit fiddly, but you know, it's a reasonably quick way of proving that one. Finding the roots of complex numbers, another one that could be useful for. So another way of finding the square root of a complex number. We're going to find the square root of 1 minus root 3i. Let's put it in exponential form. So 1 minus root 3i would be 2e to the minus I pi on 3. If I want to find the square root, then it would become root 2e to the minus I pi on 6 plus pi k, where k equals 0 and 1. E to the z, remember what we saw first thing today? E to the z plus, because it's periodic. So I can add on the 2i pi k. And we get minus I pi on 6, 5i pi on 6, and we get our result. Now, is that a great way of doing it? Because if you think about it, all we've really done is used the Wiles theorem, but in exponentials rather than the other one. So I don't know that saves us a lot of time doing it that way. There's a really nice question that appeared in last year's HSC. So the first HSC of the new course, it was a multiple choice question, you'll notice. It's question 9. You had to find the maximum value of this expression. Beautiful way of doing it. If you let z equal e to the iota theta and think about what that's saying, the modulus of z minus 2 plus the modulus of z plus 2. Well, mod z is equal to 1 because we let it equal e to the iota theta, so its modulus is 1. Therefore, z lies on that unit circle because that would be the locus of mod z equals 1. We want to find the point where the distance from z to 2 plus the distance from z to minus 2 is a maximum. All right, well, z minus 2, that's the length of the vector joining z to 2. So something like that. That would be modulus of z minus 2. Of course, it could be anywhere. I could put it over at -1 and it'd be longer. I could put it over at 1 and it'd be shorter. We're trying to find the maximum place for both of these. But there's another vector, z plus 2. It will join to -2. As the one on the left gets longer, the one on the right will get shorter as we move around the circle. So where's it going to be its maximum? Well, the maximum will be when they're the same length, which will either be at 1 or down at -1. But the length will be the same. So what is that maximum value? We can do a little bit of Pythagoras there. Square root of 1 squared plus 2 squared, root 5. Therefore, the maximum when we add them together is 2 root 5. A really neat, quick way of doing it. A lot of people might have actually, with the modulus, gone, oh, the square root of this squared plus this squared, and expanded the whole thing out and used algebra to do it. I mean, it works. But a really nice way of doing that little question. It was multiple choice as well, as I say. So you had 4 choices to sort of hone in on the solution. Anyway, there's a handful of applications of the exponential form of complex numbers.